The third operation we are going to talk about on point process are displacement. So displacement means we are translating each point of realization of point processes. So if we displace each point of each relation according to some law, x is changed to y, uh, and we collect all the displaced point, we get a new point process. An independent displacement means that each point is displaced independent of other point displacement. So this law can be random, uh, and whenever it is random, if we assume that this probability of movement y given x is independent across points, then this will be known as the independent displacement. And here we are going to mainly focus on such kind of independent displacements. So let us first take a simple case when this displacement is deterministic. Okay, so in this case there is actually no randomness because there is no consideration of independent or dependent because these are deterministic displacements. So suppose there is some function f and you take any point xi and based on its location you replace it to new location such that yi is equal to fxi. And suppose you have a point process phi with density lambda x and you displace its point uh, to yi, and suppose we take even a particular case where f is 2x, fx is 2x, so we are taking xi and we are displacing it to a new point 2xi. Okay, so it's like scaling the points. So if it's two-dimensional point, I'm scaling x and y coordinate both. So after displacement, you take each point and you displace it to 2xi, and then you collect these points back, and then from those, you get the new point process phi dash. So if phi is made from xi, the point process which is made from 2xi or which are known as yi's, this is phi dash. So basically, in short, I have doubled the distance from the origin for each point xi. Okay, but the one-to-one corresponding is still maintained. If you take these 2 point processes, there will be a map from one realization to one unique realization in yi. Okay, so you can see this is xi and I am scaled it to points. Every point will little bit move away, and this is a new point process you will get. So the question is, what will be the density and the intensity measure of this new point process? So the number of points of the new point process any set A is given as to compute the expectation measure of the new point process of set A. You take this summation of indicator yi belongs to A. Right? You go to each point and ask of phi dash and ask, are you in A? And then you take the summation and compute the expectation of it. Similarly, this is expectation here, but what I can do is, because there is a one-to-one correspondence, I can write this summation in terms of summation over points of phi also. Because each yi, there exists one xi such that yi is equal to 2xi. Okay. So this will be summation over xi's, and instead of yi, there will be 2xi belongs to A. Okay, this you can understand because see, this expectation is of any random variable is random variable multiplied by the probability that of that realization. Okay, so basically if you have a sample space capital omega and there is a random variable x omega, then the expectation of x omega would be for every omega you compute x omega multiplied by the probability of that omega, and then you add them. So here also you have one realization. To compute this, you take all the realization, take their probability, and compute this function and multiply and sum. Okay, and for the corresponding realization, there also is also xi. So instead of yi, I can also write it in terms of xi's. Okay, so let us first take a simple A, which is a ball of 0r, a ball centered at the origin with radius r, and computes its intensity measure. And yi belongs to A means yi should be inside this ball. Okay, So this is just for notation. If A you take as a ball, then yi belongs to A means you should take yi should be inside this ball. That is what it means, that yi should be inside A. And when the yi would be inside the ball, when the norm of yi should be is less than r. Okay. So what I can do is I can replace this condition yi belongs to A by norm of yi is less than r, and norm of y is nothing but norm of 2xi less than r, and 2xi less than r is same as saying that norm of xi is less than r by 2. Okay. So to compute this, I can apply Campbell theorem. For that, this will be integration over this RD of this indicator over lambda x dx. Okay, and because you are integrating over this indicator, this will be eventually this just the integration over this set. Ball 0 belongs to r by 2. So this, if you can compute, because of the definition of density, this is nothing would be intensity measure of the ball of 0 r by 2. So you can say that the number of points of the new derived point process in any ball is same as number of points in a ball of half radius in the original point process. Okay, and this can be extended to any set. So if I denote A half as the set X such that 2X belongs to A. Okay, so this if A is some set, A half is denoted by a set such that 2x belongs to A. Okay, so this means X is such that if you double it, then it should belongs to A. Okay, so this A half is nothing but a scaled version of A. So in that case, I can prove that lambda dash A is equal to lambda of A half. Okay. Now from that, let us compute the density of the derived point process. Let us assume the density of the new point process is lambda dash x. Then we know that the intensity measure of the new point process for this ball is integration of density over this ball. Okay, which is an intensity here is lambda dt. We also know that the lambda dash of ball 0r is equal to lambda of ball 0r by 2. This we have proved. So if the original density is lambda x, this from the definition of density, this should be equal to the integration of density over this set, ball 0r by 2. Okay, and now because these two are equal, this and this is equal. Okay, now what we do is to compare this and this, the inner terms, we want to compute lambda dash x in terms of lambda x. So to compare the inner terms, we need to first make sure the limits are same. Okay, otherwise we cannot compare the inner terms of two integrals. To make the limit same, what I do is I substitute t equal to 2x in this expression. So if you put t dash equal to 2x, then t would be I'm substituting here, not here. So if I'm substituting t equal to 2x here, x will be t by 2, dx would be dt by 4 because it's two-dimensional integration. Okay, so in two-dimensional integration, if you take t equal to ax, then dt is equal to a square dx. If it's a three-dimensional integration, dt would be 8 times ax. So this will be 1 upon dt. Okay, and then the limit, because here the limits are over the ball of r by 2 and t 2x. So the limit of t would be in the ball of 0r. Okay, now I can compare this and this. Okay, so once I can, because their limits are same, I can compare these two, and what I get is lambda dash t is equal to 1 by 4 lambda t by 2. Okay, so density of the new point process will be equal to 1/4 of lambda x by 2. Okay, so this I have proved by a ball of 0r, but you can also prove this actually to say that these inner terms are equal. This need to be true for every possible set A. Okay, so you can very easily write this proof in terms of general A also to complete this proof. Okay, so how do I write it? Lambda dash a equal to lambda a half. This we have proved. Now integration. This is integration over lambda dash t, and this is integration of lambda x ds over a half. And then this is nothing but saying integration of r square, indicator x belongs to a half into lambda x dx. And then I substitute, x belongs to a half means 2x belongs to a. Okay, this is by definition. A half is made from all elements such that double of that element belongs to. So x belongs to a half means 2x belongs to a. Okay, now here I substitute y equal to 2x. So I will become, this will become indicator y belongs to a, x become y by 2 and dy become dy by 4. Okay, and now I compare, I can say lambda dash x equal to 1 by 4 lambda x by 2. So a special case would be if point processor has a constant density lambda, then you can show that here this will be lambda dash equal to 1 by 4 of lambda. Okay, this means that the density will become 1/4. And in fact, if a d-dimensional Poisson point process or even a point process, then the density, new density will be 1 upon 2 to power d times lambda. So in 3D, scaling by 2 will make density by increase or decrease by 8. Okay, for homogeneous point cases, the proof may be a little bit easier also, because you can take any set, doesn't matter, it's a stationary point process. So let us take this set B0R. So in that case, lambda dash B, a number of points in the ball 0R would be integration by this. And because of the constant, this is same as saying that and because the constant, it will be just lambda into size of this, which is pi r square. So it will be lambda by 4 pi r square. And then you divide by total size pi r square, you get a density which is lambda by 4. Now next we will cover a result. So what we saw that if we displace, the density can be computed, but we exactly do not know what will be the distribution of the new point process. Okay, and in general it is hard to say that what will happen with once you displace, but for the PPP case, we can show that if you displace, you also get a PPP with little different density. Okay, so if a PPP is displaced deterministically, I'll cover first that result. Resultant one process is also a PPP, and then I will show later on that even a random displacement which is independent, you get a PPP. So to show this, if you displace a PPP deterministically, you also get a PPP. We have to start with the Laplace function. So we are scaling. Here we are taking a particular example, but this can be proved for general result also. Consider scaling of points y to factor of 2. The Laplace function of the resultant point process is given as exponential of minus summation fi's, where summation is over the new point process phi dash, and you take the expectation. Now again, as I have said earlier, you can break this integration in terms of expectation of phi dash. Sorry, so ya is actually, I can say 2xi belongs to phi and y equal to f2xi. And then 2xi belongs to phi dash means xi belongs to phi. This is a one-to-one corresponding with the realization. So I can write down this summation in the form of points over phi also. Okay, so this you can always remember. We are going to use this argument multiple times when we do displace or thin. We are having a one-to-one correspondence between the realization of the original point process and the new point process. So we can write the summation in terms of the new point process or the old point process. Okay, what is the benefit over writing over the old point process? Because we know the distribution on the Laplace function of the original or the old point process. So once we write this in terms of this, this becomes a This is a new function over xi. This is nothing but just the Laplace function of this new function f2x. So because phi is a Poisson point process, I can apply the Laplace function and I get exponential 1 minus 1 upon 1 minus e to the minus f2x lambda x dx. Okay, so this is the Laplace functional of a function f2x, okay, of a PPP with density lambda. Okay, but note that this is a Laplace function of f. What I get is a Laplace function of function f2x. Okay, so we cannot say that because this is a Laplace function of 2f, this is a Poisson point process. Okay, no, for to say that Poisson point process, you have to show that this is of the form exponential minus integration 1 minus e to the power minus fx into some lambda x dx. Okay, so lambda x can change and that will tell the density of the point process. But to say that something is of PPP, you have to show that its form should be exponential minus integration 1 minus e to the power minus fx into some function lambda that will be density into dx. Okay. So how do I convert that to this one? I can to convert f2x to fx, I can use some substitution. I can take t equal to 2x, and in that case, dt would be 2 to the power d dx. Remember, it's a d-dimensional point process, so it will be 2 to the power d dx. Okay. So if I substitute that, the Laplace function becomes exponential 1 minus e to the minus ft 1 upon 2d lambda t by 2 dt. Okay, now if I substitute lambda dash t equal to this, then what I get is 1 minus minus ft lambda dash t. Now this is a form of a Laplace function of a PPP with this density. So what I can say that phi dash is a PPP with density lambda dash x. And if it's a homogeneous, then this lambda t by will be constant lambda. So this will be just lambda upon 2 to the power d. So that will also be a homogeneous point process because that does not depend on t. So deterministic displacement of a homogeneous point process results in another PPP with homogeneous density, and that density is 1 upon 2d of the original density. Now let us take one more example, a different displacement. Consider a displacement of two-dimensional homogeneous point process to a one-dimensional Poisson point process. One-dimensional point process according to law that you take this point xi, you compute its norm. Whatever is the norm, you take the new point there. Okay. This is also a function of xi, so this is a valid displacement. But here I am also having a point process in a different dimensional space. Because the norm is a scalar value, so the new point process will only have one value, one coordinate. This is a one-dimensional point process. Okay, so it's like you have many points, and for every norm, you put it on a line. Okay, every point you compute the norm, the distance from the origin, and you put the point in phi dash at a single line at the same distance. Okay, so now to compute the density of the new point process, we have to take compute the intensity measure. Okay, and it's a one-dimensional case, so sets in the one dimension are just intervals. So I take some interval 0r and in one-dimensional space and compute the expected number of points in this space to compute the intensity measure. So the intensity measure of this set, number of points phi a of the new point process in the interval 0r is given as lambda dash is 0r is, you go to each point of phi dash and ask, are you inside this interval? So it means you should be between 0 and r. Okay, and then I can write this summation in terms of original point process. So this summation over xi, and then instead of yi, you have norm of xi is less than r. I have skipped greater than 0 because norm is always greater than 0. So So say that xi norm belongs to less than r is same as saying xi belongs to ball of 0r. Okay, so if you have this expectation and you go to each point and ask, are you there in ball 0r or not? So if you add it, you get a total number of points in ball 0r, and you take the expectation, what you get is total mean number of points in this ball of 0r, which is nothing but the intensity measure of the original point process of this set. Okay, it's a homogeneous point process. So this will be density multiplied by the size of ball 0r. So it will be lambda pi r square. Okay, instead of direct argument, you can also apply the summation of the function. So you can apply Campbell theorem and you will get the same result. So what I can say here is lambda dash 0r is lambda pi r square. Okay, total number of points in this interval 0r is lambda pi r square. So for one-dimensional process, if the density is lambda dash r, then the intensity measure should be equal to integration of lambda density from 0 to r. Okay, so note there's a one-dimensional process, the new one. So I have to deal in that dimension. If the new process was also 2D, instead of this, you will have a two-dimensional integration. Okay. So now you can, to solve this, you can compute, you can take the differentiation on both sides. So lambda dash r is equal to differentiation of the intensity measure. So d by dr of lambda pi r square, which will become 2 lambda pi r. Okay. So now you can see this depends on r. So the new point process is not uniform. Okay. So this is a different result. The original point process was stationary, but when you displace it to the lower dimension or a different dimension, the point process is no longer stationary. Okay. Here I have not proved it, but you can also prove in the similar line that the new point process is PPP if the original was also PPP. Okay. We will use a general result for the random displacement case, which will cover all these cases itself. So I'm not repeating the proof here. So now we will talk about random displacement. In random displacement, each point is displaced according to some probability law. So we can have some function which defines what is the probability that x is moved to y. Okay. So let us take a so basically it means that we are not displacing each point by a deterministic value. It has some distribution where it can go. So let us take one example here. Consider a one-dimensional point process and let hi be a random variable associated with each point xi. So for every point xi, we generate one hi. And this hi is suppose exponential random variable. And these are independent across points. And then we take the xi, multiply hi, and whatever the value we will get, we displace the point to this new location. Okay, so because hi is random, this displacement can be random. Sometimes hi is less than 1, the point will shrink. If hi is more than 1, the point will expand, it will go further away. So, and we collect all these new points and we get the new point process phi dash. So we can write phi dash equal to is made from yi such that this yi are such that hi into xi is made from points hi into xi such that xi belongs to phi. So that relation tells you the one-to-one corresponding. You take the realization, you take points xi, you take hi xi, and then this is a new point process. So owing to hi being random, the point xi is shifted to random location, which has a fixed conditional distribution given xi. Okay, so once I know xi, I know the distribution, conditional distribution of where the yi would be. Okay, but I do not know the exact location. It is a random displacement. So in one-dimensional case, where yi and xi are scalar quantities, conditional distribution given xi would be the distribution of yi given xi is 1 upon xi exponential minus yi given xi, yi by xi. Okay, this you can compute from the hi distribution. Okay, so hi distribution is exponential. So given xi, yi is hi into xi. You can scale hi by xi to get yi. So this is the scaled exponential random variable with parameter xi. So what will be the intensity measure of the new point process? For that, suppose you take a ball of 0 and compute how many average number of points are there. You go to each point and ask, are you in ball 0 and you take the expected value. And because of one realization, one-to-one correspondence between realizations, I can also sum it over all points of phi. Uh, and then the expectation will be with respect to xi and hi both, and I will ask each point, does hxi belongs to ball 0 or not? Okay. So why that? Because the if hxi belongs to ball 0 then yi belongs to ball of 0. Okay. So now I will break this expectation. Xi I will keep it outside, which is nothing but expectation of the phi, and hi given xi I will take inside. Okay. And this hi expectation will go inside also because it affects only the term corresponding to the particular value of I. So I have to compute expectation with respect to hi indicated that hxi belongs to ball 0. Okay. And when does hxi belongs to ball 0 r? It's a one-dimensional point process only when the norm of hxi is less than r. Okay. So norm of hxi is nothing but h into norm of xi less than r, and then this will become h is less than or equal to r by xi. Okay, and expectation. So this is nothing but the probability that h is less than r by xi. And what is the probability that exponential random variable is less than some value? 1 minus exponential into that. Okay, so this will become 1 minus e to power minus r by x. And then these are, so basically what I'm doing is expected over xi summation over this function 1 minus e to power r by xi. And then you can apply Campbell theorem to get this is equal to 2 pi lambda 1 minus e r by x dx. Okay, sorry, there will not be any 2 pi because this is a one-dimensional integration. Xi is a one-dimensional point process, so there will not be any 2. It is just lambda into 1 minus e to power r by x dx. Okay, now I can, to further solve it, I can substitute r by x equal to t. So this will make r by t equal to x and minus r by t square dt is equal to dx. I substitute that and I get 1 minus 2 minus t r by t square dt, and then this is 1 upon t square minus e to power minus t by t square, and r will be common outside. And then I get this one and I can integrate this. But basically you can notice whatever this is, this will be some function of some constant, which is not a function of r. So you get some c into r. So density of the new derived point process is differentiation of this because a one-dimensional process. So you just differentiate respect to r. So you get what, and this is a constant into r. So when you differentiate, you just get the constant. So the new density will be c, which is nothing but lambda into this integration. So this integration can be computed, and then that will be your density. So that was one example, but which was done performed using a particular type of scaling displacement by exponential random variable. Now, for a general case, what we talk about is the probability kernel of displacement. Okay, so displacement can be given in terms of distribution of new location conditioned on the previous location. So Px comma dy is known as the probability that a point at x can get displaced to an interval dy. Okay, so not a particular value in dy, but so some value in dy. Okay, so you for every point x, you specify what is the probability that this point will move to an interval dy. Okay, and I'm not talking about a particular location that x moves to y. because this can be a continuous type of distribution where some point can move to any space in a uncountable space. So any point in uncountable space. There you don't talk about movement of x to y, because that will have a zero probability. If you just say point x moves to a particular direction y, that may have a zero probability when the point can move anywhere in this uncountable space. So instead of that, I talk about what is the probability that x moves to some small interval dy. Okay, says that what is the probability that x moves to a ball of 0 comma. Okay, so how do I compute this? So if someone asks me what is the probability that x moves to a set A, you just divide set A into a small interval. You add the probability that x will move to those small interval, and you add them up. Okay, and you add because all those interval movement to all these intervals are they are disjoint set, so the movement is mutually exclusive. If point moves to one small interval, it cannot move to another small interval. So these are mutually exclusive. So probability that the point moves to union of any of these small set is nothing but just the summation over all the small probabilities to moving to small sets. Okay, so this will be like this, and this is nothing but probability that the after movement yi belongs to A, given that xi is equal to x. So this result you can show that for a general random displacement with the probability kernel, the displacement of a point process phi with density lambda x with probability kernel px dy will result into a point process with the intensity measure, this one. And note that this is an independent displacement, so every point is displayed according to this probability kernel, independent of other points. This will be that the expected number of points in the interval set dy is given as integration over all points or space lambda px dy dx. So you can interpret in the following way. You are assuming the points can be anywhere, the original point can be anywhere in the space Rd, and the expected number of points in a set interval dx is lambda x dx. So these many points are there in the set dx. Okay, and this set is around the point x. So around a point x, there is a small interval dx, and the number of points in that set is lambda x dx. And they move to set dy with this probability. So expected number of points which have moved to set dy is given as lambda x dx, this is the original number of points, multiplied by the probability they will move to a set dy, which is p x comma dy. And then you integrate it, the original point can be anywhere. From any location, the point can move to dy. If you add all those small intervals, the total number of points which are now in set dy is given by this integration. And this is a general result. It will also cover deterministic displacements if you replace probability laws by a deterministic law. Now we will cover a result for PPP. We show that if we displace a PPP with density lambda x according to a probability kernel px comma dy, then it will also result into a PPP with intensity measure given it's by the following formula. So what does it basically mean? That if you displace PPP, you get a PPP. Okay, this result is not generally true for other point processes. If you displace them, you may get a very different point process. But here, the PPP has this nice property that if you displace its point, the resultant is also a PPP. And of course, I am assuming a independent displacement now. So how do I prove this? Again, we go back to Laplace functional. The Laplace function of the resultant point process is given by this. This is expected exponential minus summation over all points of phi dash f phi I exponential. Okay. Now what I do here is I first convert it to a product form. So this will become E5 dash product over all points e to the power minus FYI. Now note that phi dash is a map from sample space, but it can also be constructed by uh, going to phi and then coming to phi dash according to that probability distribution. Okay, so you can first map to phi, and then from that phi you map back to phi dash. Okay, according to some distribution. So what I do is here I am using two conditional distributions. Sorry, I'm using the law of conditional distribution. Is that uh, inside there is a expectation phi dash given phi, and then the outside there is a expectation uh, with respect to phi. Okay, so this is a typo. This is not phi dash. This is phi. So inside this is phi dash given phi, and outside I decondition with respect to phi, and inside there is a product over phi dash E F Y I. Okay. Now, if I know xi original point process, which I am conditioning on, then I know that there is a one-to-one correspondence between the points of phi and phi dash. So instead of writing the product in terms of points of phi dash, I can write it in terms of product of over points of phi. So I can say it's a product on xi belongs to phi, E of minus of phi. Okay, and this yi is generated from xi according to some distribution. Okay, so if I have to compute the expectation of this with respect to phi dash given phi, okay, and then you can notice that uh, because this product is over xi belongs to phi, and phi is already given, so this number of product terms are in deterministic. Okay, so given phi, the number of product terms are deterministic, so I can take this product sign outside the expectation. Okay, so outside expectation xi belongs to phi. Again, this is phi, not phi dash. So to compute the expectation with respect to phi dash given phi, yeah, and we notice that although this is phi dash given phi, expected with respect to this, but only terms which are needed here is xi and yi. Okay, yi from the phi dash and xi from the phi. So this phi dash given phi actually means yi given xi, because no other point of phi is required to define this expectation. And also this is only a function of yi, so we don't have to take it expectation with respect to other random variable. So this is nothing but EYI given xi, E of minus FYI. Okay. And what is this expectation of E minus FYI given xi? We know that given xi, yi can take probability this. So if I divide the complete space into small interval of dy, the probability that the yi takes a value in dyi is this, and the value, if it takes a value in dyi, the value of this term would be this. So the expectation is summation over all those small intervals of the actual the value at that point multiplied by the probability that it takes value around that point. Okay, so this is an integration of EF minus Fy into probability that yi belongs to dyi given xi. Okay, so probability that given xi Fy takes value Fyi is this probability. So I multiply probability by the actual value and add it over all small intervals. So I get the expected value of e to the power minus Fyi. Now remaining is to compute the expectation of this term with respect to all xi's. Okay, so now if you notice this term is nothing but a function of xi only. Okay, because for yi I have integrated it over dys, so this whole thing is a function of xi only. So I can assume this is gxi function. So this is nothing but expected of product of function gxi. And notice that gxi is given by this form. It is e to power minus fy px dy. So now this is expectation of product over function. So this is can be computed by PGFL of phi, and phi is Poisson point process. So this is I can apply PGFL of Poisson point process to further solve it. So if when I apply it, I get this one, and then I put the value of gx by this. So I get exponential 1 minus integration over e to the power minus fy px dy dx. Okay, and just notice this integration is over y and this integration is over x. And it may happen that y is actually in Rn and x is in Rm, so they can have a different dimensions. Okay, so you can always displace point from one dimension to into another dimension. So now to further solve this, what I do is I first notice that 1 can also be written as integration of px dy over all y's. Okay, so why this is 1? Because given x, the probability that the point will move to dy is this one. And if I add it over all the set, I just get probability that after moving from given x, the point will move to one point in Rn. Okay, and of course it will move to one point in Rn, right, with one probability. So this total probability would be px comma Rn, which is 1. Okay, and by writing this one, what I'm doing is just that I can take x comma dy common. Okay, so I notice this, and then I take px dy comma common. So what I get is integration over y. So integration over x, integration of y, and this will become px comma dy 1 minus e to the power minus fy and dx. Okay, now I change the order. I keep the y outside and x inside. So what I get is integration over y 1 minus e to the power minus fy, because this is no longer a function of x, and then this is px dy dx. Okay, so I've explicitly write y and x just to know that which integration is respect to what. Okay, and now if I let lambda px comma dy dx equal to lambda dash dy, which is from the original definition, then what I get is exponential minus 1 minus exponential fy lambda dash dy. Okay, and this is nothing but the form of PGFL of a PPP with density this. So what I showed is the phi dash is also a PPP with this density. So where we can apply this results that displays PPP is also PPP. Suppose we take an example of random walk over PPP. So there is a original point process is a PPP, and then each point at every time step, each point moves randomly into some direction. Okay. So each point of a homogeneous point process is shifted by a random amount as per the following law to get a new point process at the next time step. So there are time steps. So at ith time, if the location is xi, the next time the location would be xi plus ni, where ni is a Gaussian random variable with some mean and variance. Okay, so every time the point moves around itself with a step which is Gaussian distributed. Okay, so now you can notice that for every step, the condition on xi, the point moves to a new location yi according to a fixed distribution. Okay, and it does not depend on any other point. So it's an independent displacement. So if someone asks you at the next time step, what will be the point process look like? If I collect the new location of points, how does it look like? So that will again be a PPP because yi are independently displaced points. So YIs are also PPP. Okay, so this can be generally extended to say that random walk occurs over n instants. Okay, that at the next step also the point again moves independently and then again moves. Then you can also show that even after n conjugated random walks, the resultant is a PPP. Okay, so how does this help us in modeling wireless? Suppose you assume the mobile devices are PPP and then users are actually moving in the space independently. uh, then like the next time step also, the points will look like a Poisson point. Okay, so the PPP has this nice property which we have seen. The superposition of PPP is also PPP, the thinning is a PPP, and the displacement is also PPP. So because of this, PPP models are very popular in modeling of wireless, because once you know the tools for the PPP, uh, movements of the nodes or the thinning of the nodes, or even a coexistence of multiple types of node does not affect the overall distribution. The same results can be applied uh, also. So we have seen in the past that by definition of Poisson point process, if there are two disjoint sets A and B, then the points in A are independent of points in B for a Poisson point process. So let us see an example based on this. Let A be a ball of radius r and let B the complement of it. So whatever is outside this ball of radius r. And let phi be equal to phi intersection B. So remember, phi is a set of points and intersection with B means you are only taking points which are in B. Okay, so phi B is nothing but the PPP, but you exclude the points which are not in B. And someone asks you find a distribution of minimum of distance of xi or minimum of norm of xi among all points of phi B. Okay, so norm of xi is the distance from the origin, and minimum means you want to find the one which is closest to the origin among all points in phi B. So basically what we are interested in, finding a distance of the closest point in the set B from the origin. And we want to find its distribution. So the question I want to ask here is, will this distribution change if we condition on any event that happened in set A? For example, what will be the distribution of minimum xi among all points of phi B, condition on the event that there are 5 points in set A. Okay, so if there are 5 points in set A, then the minimum point in xi is actually the 6th point of the PPP. If you consider PPP in the complete space, then it will be the 6th point. So the question is, if there are 4 points, then it will be 5th point. So the number is changing depending on what is happening in A, but that there's a distribution of this point, the closest point of phi B changes depending on how many points are there in A. Okay, so I say closest point in B, but if I talk about that will always be the closest point. But when I talk about the complete PPP, whether it's a 6th point, a 7th point, that number changes depending on the number of the set A, number how many points are set in set A. Okay, so I want to ask this question: condition on there are 5 points. What is the probability distribution of the 6th point? Okay, uh, 6th closest point. It is the same thing as saying, because there condition that there are 5 points in A, I want to ask what is the distribution of 6th point. That is same as asking this question: what is distribution of the closest point? Condition on the event that there are 5 closest point of B, condition on the event that there are 5 points set. And then I want to change my question. I want to ask what is the distribution of 4th point, condition and there are 3 points in A, or what is the distribution of n plus 1th point, given that there are n points in A. My question is, does the answer depends on n? Okay, so what you can say is A and B are independent and disjoint. So whatever is happening in A, it should not affect B. Okay, so the probability that of distribution of the distance of the n plus 1th closest point, condition that there are n point in the ball of radius r, that distribution should not depend on. Now, what if I want to change this question a little bit? Instead of A being a deterministic set, I want to make it random. Okay, so let A be a ball of radius equal to R1, where R1 is the closest point of PPP from the origin. Find the closest point in B, which is complement of A. So now here A is random. A is, in the previous example, A was a ball of radius R. And then we can say because A and A complement are independent, the PPP in A is independent of PPP in B. But here, A is not independent. A is the ball of radius equal to R1, the closest point of PPP. So I want to ask what is the closest point in B given, yeah, given A. First B depends on A. So now basically you want to ask is what is the distribution of second closest point? Okay. And suppose, yeah, condition on the first closest point. A is a random set, B is a random set. So R, A and B are independent. Sorry, PPP in A is independent of PPP in B. So answer is not that straightforward. To understand this, first we need to know what is a stopping set. So let me first define what is a random compact set. In a point process phi, any subset of RD is called a random compact set if S is a function of phi. It means as for different realization you may get different S. Okay, and if this S is a compact set that is a function of relation of phi. So so S phi is a compact set always for any realization, and it's a random compact set if this value changes as a function of realization. So for instance, the ball of 0 to R of fixed R radius is not a random compact set because it does not depend on relation of phi. But if I say the ball of B, R0, where R0 is the closest point, that's a random compact set because it is compact. And its realization, it depends on the realization of phi. If the closest point is very far away, this ball will be big. If the point is close by, the point will be small. So note that phi is used to denote the point process, while phi is being used to denote the particular realization. That is a general notation we have been using. So a random compact set S phi is called a stopping set if one can say whether the event S phi belongs to K has or has not occurred, knowing only the points of phi in K. And this should be true for every realization of phi. So for every realization, the random compact set S phi is you get I should be able to tell whether this set belongs to K, is inside K or not, just by knowing the points of phi in K. Okay, which means and this is true for any K. So I don't need to know the point outside K to tell whether this compact set lies inside K or not. Okay, so let's see an example here. Consider the kth smallest random ball. which contains exactly k closest point. Okay, so I find the k closest point and I create a ball just touching that, so that there are exactly k points in that ball. So let R k is the minimum R says that phi b 0 R k is k, and then this ball of at origin with radius R k is a random compact set, right? Because it's random, it's compact set. The question is this a stopping set? So for this to be a stopping set, you should be able to say that this ball lies inside K. I can tell that best by knowing the points in K for any K. Okay. So how do I show this? So let's see an example here. Suppose K is ball 0, R. Now let us start growing the ball 0, R centered at the origin, and we increase the radius r from 0 until the moment either one of these two things happen. Either it accumulates k or more points than this two, or it hits the boundary of ball k. Okay, so you take a general. Okay, so I don't need to have this as a fixed ball. I will take a general k actually. Yes, I take a general k. It should be, I need to show it for a general k. So it either accumulates the k or more points, this ball, or it hits the boundary of ball k. If one happens, this means there are k points in the ball of 0r, and this one happens means it has not hit the ball of k. So which means before hitting the ball of k, this ball has accumulated k points. Okay. Uh, and so this means the compact set which has exactly k point should be totally inside the ball of k. Okay. And note that because we did not cross k, we are only deciding our uh, decision based on the points inside k only. Okay. Now, if 2 happens that before accumulating k point it has hit the ball of k, then I know book I confirm that this cannot be inside k. Okay, because it means there is at least one point out of k which is outside k. Okay, it is not, otherwise it would have found in k. Okay, so you are increasing this ball, and if there are not k points and it has already hit k. It means if you create, whenever you get that gate point, if you create the ball, that ball is of course going to be outside K at some locations. So in each of these cases, we are able to completely tell whether the ball belongs to K or not. This compact belongs to ball or K or not, and just by knowing the information about points inside K. So this means this compact set is a stopping set. Okay. Similarly, ball at origin whether it is equal to the third closest point, you can exactly say the same thing. Okay, we know S is subset of K when K contains origin and K contains 3 points. Okay, so if K satisfies any of 3 properties, then we know that S well belongs to K, and we don't need any other point outside K. Okay. Now what is not a stopping set? Let's take a ball at the first point with radius upside. So for every realization, we find the closest point and take a ball upside and outside it. Okay. Now if you take this set K, whether this ball belongs to this or not. Here in this case, this ball belongs to this set because the closest point was inside it. Okay, but if you look at this set K, I can only I need to only have information about the points in this set K. Okay, but just looking at these points in this set K, I cannot determine whether the closest point is inside this set or not. Okay, because suppose the closest point is here. Okay, and I have no information what is happening outside this set K. Okay, uh, to determine whether this point is the closest point or not, I need to construct a ball of the radius and then see if there is any point in that or not. So to know that, suppose there is a point here in K. So to know that this is the closest point or not, we need to know the complete information in this ball. Right? If there is any point inside this, it means this is not the closest point. So we need information about the point which are outside. So this will not be a stopping set. So once we know some set is stopping set, then we can state the independence property. So let me first say that, let me first formally state the disjoint independent property. When we say that the disjoint, if they are disjoint set A1, A2, A3, then we say that phi A1, phi A2, phi AM are independent for mutually disjoint sets A1, A2, and AM. So the other way to state the same thing is, let B be a set, B be a set, and F be a function of PPP. So it's a property of PPP. So we know that expected of F function of that PPP is equal to expectation of function of another derived point process, which is constructed in the following way. Phi intersection B means phi which is occurring in B. So all the points of phi which are in B. And then phi dash is an independent copy of phi which has the same distribution as phi, but is an independent copy. So all the points in phi, these are independent of phi. So you take that copy and take intersection with B complement, which means you take all the points of this independent copy outside B. Okay, and then you take the union. So you construct a new point process, which and then you take the function of that and compute the expected value. So which means that if you are interested in any property expected value or the expected behavior of any property or the function of PPP, then you can get the same value by taking the PPP inside B and replacing the outside PPP with an independent copy. Okay, so you can replace the PPP outside a ball B by independent copy of PPP, and the result will not change. Okay, so this can be extended for a stopping set, that instead of deterministic B, I can use a stopping set, which means if there is a stopping set as phi, then whatever is the PPP inside it, and the outside it, I can replace the PPP with independent copy, and the combine this way, whatever PPP I get, the prop distribution of the same property over this does not change, it's same thing. This basically means that if, as I said, if the A and B are disjoint sets, sorry, A and A complement are disjoint sets, so whatever is point process inside A, that does not affect what is the point process in A complement. Similarly, this property can be replaced, will also hold true if A is replaced by a stopping set. So whatever point process which is happening in stopping set is independent of what is happening outside stopping set. So where can we use this result? So let us compute the second closest point distribution condition on the first closest point. So if R1 is R small r1, the first closest point is located at R1 distance, then what is the probability the second closest point is more than R2 distance? Okay, so how do we compute this? So if R2 is more than R1, then probability that R2 is more than R2 given R1 is at R1, which means if, so I construct this ball of R1 and there is one point exactly at this boundary. What is the probability the second point is outside this R2 ball? So I construct a ball of R2 radius, and what is the probability that R2 is more than R2, which means the second point is outside this ball. Okay, so the first point is at this boundary and the second point is outside this ball, and we know that there is no point inside it. So second point outside ball means second point should be outside this ring. Okay, second point cannot be inside this, that we know. Second point or the first closest point of this complement ring should be outside this ball. Okay, so the probability will be same as there is no point in this ring. Okay, so what is the probability there is no point in this ring is e to power minus lambda into area of that ring, and area of ring is pi r2 square minus r1 square. Okay, and if R2 is smaller than R1, then the probability is 1, because of course the second, if I take R2 is smaller than R1, then of course R2 will be more than R2 will be more than R1, so R2 will of course be more than small r2. So this is what we get. Okay, so alternative we can also write this way: probability R2 is more than R2 is equal to, given that R1 is at R1, is equal to e to the minus lambda pi max R2 square minus R1 comma 0. Okay, yes, and then so we do not require any independence property here, but to proceed further, if we want to compute the marginal PDF here, marginal CDF of R2, we need to integrate this with respect to distribution of R1, because this is a conditional distribution. So we have to first compute the joint distribution and then integrate it with respect to that to compute the marginal distribution. Okay, and for that we have put this lambda pi r2 square minus r1 square, and pi r1 we already know this, and then we have integrated this this expression over the joint the distribution of r1, and then we have gotten this result. So this is the probability. If you look at probability that R2 is more than R2 is a probability that there are at least one point, at most one point in the ball of radius R2. Okay, if there is more point than that, then of course the second closest point will not be more than R2. Okay. So where did we use the stopping set property? Here, when I said there is no point in this ring shape, this thing, even if we are conditioning that there is a point at this boundary, we want to compute there is no other point in this ring. Okay, so here we are using this property that condition on this, the distribution outside this ball does not change. It remains like a independent PPP. So this is a random closed set, compact set, and still this is independence holds because this is stopping set. So because even conditioning on that R1, the second point is at R1 distance, this is whatever the point distribution in the ring does not change. So the probability that there is no point in this ball still remains, in this ring still remains as unconditional PPP, which is given by this void probability.